Welcome. My name is Rafiullah Omar, and I am pleased to present our research conducted at FrAmeLab, University of L'Aquila, together with Professor Henry Muccini. Our topic is greening the AI, evaluating tokenization method for energy efficient NLP. Artificial intelligence is being used across many critical sectors, from healthcare and transportation to education, media, manufacturing, and finally agriculture. As AI becomes more pervasive, so does the need to consider its energy footprint, especially for large-scale NLP applications, and specifically for the large language models, LLMs. And nowadays, there are a lot of models that work on the text, that works on the videos, that works on the different type of inputs. They consume a lot of energy. If we see as some of examples, for example, we see here ChatGPT training. ChatGPT-4 used 50 gigawatt hours of energy, which is enough to power San Francisco city for 3 days. And training ChatGPT cost over $100 million. And if you go to as a task, when we ask GPT, when we ask different models, for example, creating a single 5-second AI video can use 3.5 gigajoules, equal to riding 38 miles on an e-bike, running a microwave for over 1 hour, which is too much energy. Same here, if we say the start gate energy, if we see like writing an email by ChatGPT, a short email, 100 words email, it consumes 519 milliliters of water. So without a policy change, AI could emit 1.5 gigaton of carbon dioxide by 2030, matching at least 5-year total energy emission. And it is becoming more concerning when we see that inference, not training, now makes from 80 to 90% of AI energy use. So what does this mean? This means that the more the number of people get increase using ChatGPT, using different models, the energy consumption increase with that. Before, the focus was on the accuracy of AI model. They were concerning about how accurate we can make the AI models to make the prediction accurate. And when we only focus on the accuracy of AI model, this concept is called red AI. Researchers, industry, academia, they were focusing on the accuracy of AI model. And this concept is all called red AI. But now the focus is shifted from only focusing on the accuracy. They are also focusing on the efficiency or on the energy consumption of AI model. In this concept, when we focus both on the efficiency and accuracy, this concept is called green AI. So that the heart of, or the main focus of green AI is to balance the accuracy and energy efficiency of AI models. Here is the formula for the cost of AI models. We see that that cost, or the total cost of AI model, is growing linearly with E. E is the cost of processing a single example, and it depends on the second factor, which is D. D is the size of the data set, and the third factor is H, the number of hyperparameter experiments. So these are the 3 factors that affect the cost of AI models. The first one is E, D, H. If we manage to somehow reduce any of them, in fact, we can reduce the overall cost. So how to reduce that? there are three dimensions from which we can approach green AI. The first dimension is data-centric. In the data-centric approach, the focus is not on the model, the focus is on the data. How to manipulate data in a way to reduce the energy consumption. And this reduction must not be in the cost of reducing the accuracy. If we reduce the energy consumption, it doesn't mean that we have an open hand that we can sacrifice accuracy. No, reducing energy while maintaining the accuracy at an acceptable level, or even sometimes if we risk a very negligible accuracy, that is okay. But also that depends on the cases, that depend on the scenarios, not always. In the third, in the model-centric approach, the focus is on the model. In the third dimension is the system-centric approach. Our focus is on the data-centric approach. We are approaching the data-centric dimension to reduce the cost of AI models. Why data-centric? Let's take a sample examples. We see in this example that if we have a query with small number of tokens, and if we have a query with more number of tokens, like here, it is a typical query. Typical query, we can say something less than 10,000, maybe 1,500, a query with 500 tokens. If we ask a typical query, let's suppose with 500 tokens from ChatGPT or from any other model, and if we ask a query with 100,000 tokens, here, if the number of tokens increase, the cost per token also increase. And what is that number or percentage? It is 90%. So if the number of token increase from 1,000, let's suppose typical query, to 100,000, the per token cost, processing cost, increase 90%. So it means if we reduce the number of tokens, we can save energy. And to create the tokens, there are three different tokenization methods that generate tokens. One tokenization method is word-level tokenization, where in the word-level tokenization method, the number of each word is treated as a token. In the subword level tokenization, it lies between character level and word level. Each subword is treated and considered as a token, and how is that subword decided? That is something different. And in the character level tokenization, each character is considered as a token. So there are three tokenization methods: word level, subword level, and character level tokenization. This tokenization method also impact some other parameters, some other hyperparameters in different models. For example, this is the vocabulary. We have in NLP models, we always have a vocabulary. In the size of this vocabulary, actually, what is this vocabulary? This vocabulary contains the unique words in the data set. And the number of these unique words depend on the tokenization methods. If the tokenization method is word level, each word here is a record. And if it is character level, each character is in the vocabulary. And if it is subword level, then each subword. So the size of the dictionary, the size of vocabulary depends on the tokenization method. And there are some other different hyperparameters that are being affected by the size of the vocabulary. Tokenization methods are not only in the RNN or BiLSTM or in the GRU, but it is even there in the architecture of most of the modern LLMs. Transformer architecture is an architecture that most of the modern LLMs are based on. And we see in the transformer architecture that this is a typical encoder-decoder transformer architecture that we see here when we encode. In the encoder, first we tokenize our words. And in the tokenization, we have three choices. Which tokenization method do we use? And then we, in the decoder part side, or in the decoder side, we also have tokenization. First, we tokenize our target language. And also in the decoder, when we provide the output, even here we have tokenization. So there are three processes in the encoder-decoder transformer architecture where tokenization is involved. So what is our objective? What we do with tokenization? We compare these different tokenization methods based on the energy use during tokenization, and during training, and during inference. So there are three places where we investigate the tokenization. We investigate tokenization during tokenization, that how much energy do each tokenization method consume when they tokenize the dataset. And second, after tokenization, how does these different tokenization methods impact the training energy and also the inference energy? And then we investigate the accuracy of model. So to answer this, to achieve this objective, we have four research questions. The first research question, in the first research question, we compare the energy consumption of different tokenization methods itself when they tokenize the dataset. And in the second research question, we investigate the impact of these different tokenization methods on the training energy consumption, the training phase of the model. And in the third research question, we check and we investigate that how do various tokenization methods affect energy consumption during the inference phase of the model. And finally, we check and we investigate, we analyze how do these different tokenization methods impact the accuracy of the model. Our experimental setup is controlled to answer those four research questions. We selected a model which is called BiLSTM with some default hyperparameters. Hyperparameter tuning is not part of our research. It is not within the scope of our research. Here we have, in this model, we have two layers, each with 128 units, and the size of the embedding is 300. The dataset, we selected three datasets to increase the generalizability of our result, our output. And the token padding used for word level is 500, for subword level is 1000, and for character level is 1300. And the hardware used is a 16 GB RAM and RTX 4070 GPU and 1 TB SSD. The energy tool used was CodeCarbon. CodeCarbon is a library that is used to measure the energy consumption. And this is the overall flow of our experiments. And the total number of experiments that we ran are 135. Because we have three tokenization methods and we have three datasets, and we repeat each experiment 15 times just to get consistent result. So the total number of experiments we run are 135. This is a result of our investigation, our research. In the result of the first research question is shown in this diagram. We see that the subword-level tokenization method consumes the most of the energy during the tokenization itself. And these two other methods consume less. Word level is the most energy efficient, while character level is also energy efficient. It consumes a bit more than word level. Here in the word level, it consumes 43 joules, and here in the character level, it consumes 48. So the difference is almost 5 point something. But when it comes to subword level tokenization, it consumes 150. So the difference is too much. It consumes significantly more energy compared to word level. And if we quantify the result, we see that subword level tokenization consumes 248% more energy compared to word level tokenization. And when it comes to the second research question, result of second research question shows that character level tokenization consume more energy during training the model. Why? Because character level increase the size of the input tokens, and we saw in the previous example that increasing the size of the input tokens increase the per token energy consumption. And this result is consistent with that example. And we see that word level tokenization is also here the most energy efficient method. And if we quantify the result, we see that the word level tokenization the character level tokenization method consume 126% less energy compared to word level tokenization. And when it comes to the inference energy, we saw that character level tokenization consume more energy compared to word level tokenization. And if we quantify this, we see that character level tokenization consume 59.3% more energy during inference compared to word level tokenization. And finally, when it comes to the F1 score, we see luckily that word level tokenization is the more accurate method. And if we use the word level tokenization for tokenization, the model is more accurate compared to subword and character level tokenization. And to quantify the result, word level tokenization compared to character level, character level tokenization word level tokenization consumed 14.7% more accurate result, give us more accurate result compared to character level tokenization. The main outcome or the main result which you can also conclude is that word level tokenization is the most accurate and consume less energy during tokenization, training, and inference. In the future work, we will extend these experiment and these work to the transformer models. We will explore some hybrid methods, and we also investigate the effect of vocabulary size on the accuracy in energy. Thank you for further details. In case if you'd like to connect or learn more, feel free to scan the QR code to reach us on LinkedIn. We are always happy to discuss ideas around green AI and sustainable AI, sustainable LLM, sustainable AI agents, sustainable NLP, and more. Thank you for your attention.